Innovations is a vibrant R&D ecosystem comprising institutes of higher learning and research facilities, working to ensure that technology paves the way ahead for the aquaculture industry. The Singapore Food Agency has supported both land-based farms as well as coastal farms in a sea of ways, from co-funding R&D to supporting the adoption of new technology and future-ready solutions. By utilizing innovation, technology, and research to maximize efficiency and productivity in our offshore and land-based farms, we will be able to grow more with less and achieve our 30 by 30 goal, bringing Singaporeans a safe and secure supply of food for years to come. Singapore is a small urban nation with around 1% of our land set aside for agriculture. Where can we grow our food? In 2019, the Singapore Food Agency put forward an ambitious goal for sustainable food security in Singapore.
30 by 30.
30 by 30.
30 by 30.
Currently, less than 10% of our nutritional needs are produced locally. SFA aims to increase local production to meet 30% of Singapore's nutritional needs by 2030. Aquaculture is a pillar of Singapore's agri-food industry, striving towards this goal by employing climate-resilient, resource-efficient, and sustainable technologies. At the forefront of these innovations is a vibrant R&D ecosystem, comprising institutes of higher learning and research facilities, working to ensure that technology paves the way ahead for the aquaculture industry. The Singapore Food Agency has supported both land-based farms as well as coastal farms in a sea of ways, from co-funding R&D to supporting the adoption of new technology and future-ready solutions. By utilizing innovation, technology, and research to maximize efficiency and productivity in our offshore and land-based farms, we will be able to grow more with less and achieve our 30 by 30 goal, bringing Singaporeans a safe and secure supply of food for years to come. Singapore is a small urban nation with around 1% of our land set aside for agriculture. Where can we grow our food? In 2019, the Singapore Food Agency put forward an ambitious goal for sustainable food security in Singapore.
30 by 30.
30 by 30.
30 by 30.
Currently, less than 10% of our nutritional needs are produced locally. SFA aims to increase local production to meet 30% of Singapore's nutritional needs by 2030. Aquaculture is a pillar of Singapore's agri-food industry, striving towards this goal by employing climate-resilient, resource-efficient, and sustainable technologies. At the forefront of these innovations is a vibrant R&D ecosystem, comprising institutes of higher learning and research facilities, working to ensure that technology paves the way ahead for the aquaculture industry. The Singapore Food Agency has supported both land-based farms as well as coastal farms in a sea of ways, from co-funding R&D to supporting the adoption of new technology and future-ready solutions. By utilizing innovation, technology, and research to maximize efficiency and productivity in our offshore and land-based farms, we will be able to grow more with less and achieve our 30 by 30 goal, bringing Singaporeans a safe and secure supply of food for years to come. Singapore is a small urban nation with around 1% of our land set aside for agriculture. Where can we grow our food? In 2019, the Singapore Food Agency put forward an ambitious goal for sustainable food security in Singapore.
30 by 30.
30 by 30.
30 by 30.
Currently, less than 10% of our nutritional needs are produced locally. SFA aims to increase local production to meet 30% of Singapore's nutritional needs by 2030. Aquaculture is a pillar of Singapore's agri-food industry, striving towards this goal by employing climate-resilient, resource-efficient, and sustainable technologies. At the forefront of these innovations is a vibrant R&D ecosystem, comprising institutes of higher learning and research facilities, working to ensure that technology paves the way ahead for the aquaculture industry. The Singapore Food Agency has supported both land-based farms as well as coastal farms in a sea of ways, from co-funding R&D to supporting the adoption of new technology and future-ready solutions. By utilizing innovation, technology, and research to maximize efficiency and productivity in our offshore and land-based farms, we will be able to grow more with less and achieve our 30 by 30 goal, bringing Singaporeans a safe and secure supply of food for years to come. Singapore is a small urban nation with around 1% of our land set aside for agriculture. Where can we grow our food? In 2019, the Singapore Food Agency put forward an ambitious goal for sustainable food security in Singapore.
30 by 30.
30 by 30.
30 by 30.
Currently, less than 10% of our nutritional needs are produced locally. SFA aims to increase local production to meet 30% of Singapore's nutritional needs by 2030. Aquaculture is a pillar of Singapore's agri-food industry, striving towards this goal by employing climate-resilient, resource-efficient, and sustainable technologies. At the forefront of these innovations is a vibrant R&D ecosystem, comprising institutes of higher learning and research facilities, working to ensure that technology paves the way ahead for the aquaculture industry. The Singapore Food Agency has supported both land-based farms as well as coastal farms in a sea of ways, from co-funding R&D to supporting the adoption of new technology and future-ready solutions. By utilizing innovation, technology, and research to maximize efficiency and productivity in our offshore and land-based farms, we will be able to grow more with less and achieve our 30 by 30 goal, bringing Singaporeans a safe and secure supply of food for years to come. Singapore is a small urban nation with around 1% of our land set aside for agriculture. Where can we grow our food? In 2019, the Singapore Food Agency put forward an ambitious goal for sustainable food security in Singapore.
30 by 30.
30 by 30.
30 by 30.
Currently, less than 10% of our nutritional needs are produced locally. SFA aims to increase local production to meet 30% of Singapore's nutritional needs by 2030. Aquaculture is a pillar of Singapore's agri-food industry, striving towards this goal by employing climate-resilient, resource-efficient, and sustainable technologies. At the forefront of these innovations is a vibrant R&D ecosystem, comprising institutes of higher learning and research facilities, working to ensure that technology paves the way ahead for the aquaculture industry. The Singapore Food Agency has supported both land-based farms as well as coastal farms in a sea of ways, from co-funding R&D to supporting the adoption of new technology and future-ready solutions. By utilizing innovation, technology, and research to maximize efficiency and productivity in our offshore and land-based farms, we will be able to grow more with less and achieve our 30 by 30 goal, bringing Singaporeans a safe and secure supply of food for years to come.
Well, good morning, good afternoon, and good evening, everyone. Thank you very much for joining and welcome to the final day of sessions for the World Aquaculture 2020 webinar. Today, there will be two sessions over the next 2 hours, with session one focusing on novel aquaculture production technologies and automation, and session two on nutrition of fish and shrimp. To introduce myself, I am Dean Jerry from James Cook University in Australia, and along with my co-moderator, Dr. Leow Basti, former assistant professor at the Tokyo University of Marine Science and Technology and International Program Chair of World Aquaculture Singapore 2020, we will be chairing the first session, which will comprise two presentations. One from Mr. Ban Tat Leow on floating closed containment systems in aquaculture, and the other from Dr. Romi Novriadi on production technologies used in the Southeast Asian shrimp industry. As I'm sure all the webinar delegates are aware, aquaculture is undergoing a recent technological renaissance, with parts of the industry moving from culture systems and methodologies that are based on low utilisation of technology to a position where technological innovations are being developed and integrated into routine production practices. Some of these developments involve new and novel offshore containment aquaculture systems that allow farming in virtually any water system, to the use of artificial intelligence and machine learning to predict feeding behaviour and well-being of the culture species. These new innovations are being delivered to increase control and efficiencies in our production, as well as to limit risks associated with disease and biosecurity and environmental impacts. In today's first session, you will hear about some of these technological applications, starting with innovation that is particular reference and important to Singapore's 30 by 30 food security agenda, that of closed containment barge production systems. Before I introduce the first speaker, a bit of housekeeping. You can put questions to the presenters by asking them in the Q&A tab of the webinar, which is a little button with a question mark on it that you can click and pose a question. At the end of the presentation, we will hopefully have time to put these questions to the presenters so that they can address them directly. Okay, to our first speaker for the session. It is my pleasure to introduce Mr. Ban Tat Leow. Mr. Leow has over 40 years of experience in the marine and offshore industry in Singapore and overseas, and is the founder and CEO of AME2, the Aquaculture Centre of Excellence and Nature Resources Aquaculture. He is the inventor of the Noah's EcoArk floating closed containment fish farm. And EcoArk is a sustainable farm that combines proven marine and offshore technology with aquatic health and post-harvest technology, harvesting green energy that makes it potentially the farm of the future. He is also the inventor of the Lift Dock, which is an innovative offshore platform. Mr. Leow holds a master's degree in business administration and a first-class marine engineering certificate of competency, and was the president of the Society of Naval Architects and Marine Engineers in Singapore, and also served a total of 39 years in the Ministry of Defence and the Singaporean military as National Serviceman Chief Operating Officer. Mr. Leow's presentation is titled Opportunities for Floating Closed Containment Systems for Fish Farming, and I welcome you to listen to it now.
Yeah, good afternoon, ladies and gentlemen. I am pleased to be here today to present the future of a floating closed containment system. And I will now present quickly on the introduction of what is closed containment system. There are two types of sea-based aquaculture system, the open containment and the closed containment. In the open containment, one rely entirely on the external natural ecosystem for the temperature, for oxygen, by having a good site location. In the closed containment, it basically separates the fish from the external sea environment. In the FCCS, they use the proven technology in the re-aquaculture system, or in the FCCS, you can use a flow-through system. It can be flexible, it can be rigid, it can be semi-flexible. The water treatment of the inlet water and the treatment of the water outlet is very important. At this juncture, I'd like to thank Professor Dr. Wong Chin Ming from the University of Queensland for co-authoring this article with me, and the article can be found in the website as shown below. There's always a concern on the total cost of infrastructure and its operation. That means the capex cost, or how much is your cost per kilo in your production, and how much will be your opex cost per kilo in your production as well. Now, and then the next is the availability of the infrastructure in open net cage, or be it a closed containment system. Is it durable, and what kind of power are you using? Is it off-grid power, or do you generate your own power, or do you use green energy? And I think the next part on the infrastructure is the ease of its construction, how difficult it is to mobilize the material to get it on site. Now, the next thing is, how do you reduce the dependence on external oxygen cylinder, or rather should you generate our own oxygen is another consideration. Lastly, the most important is sustainability. It's all spoken, but how true are we in sustainability will depends on how we produce fish at every stage of our production. Lastly, on the social part is, do you create employment for the people where you farm? One have to design and develop a closed containment system that is not pollutive. Now, the cost of production is the next one that I mentioned earlier. It must be comprehensive all the way from farm to fork and to its value chain, or being able to reach the customer, and in its biological and ecological performance. Manpower saving. Are you saving manpower? Are you constantly relying on more manpower to do cleaning of the net? Or do you use the manpower to do the aquatic health of things? Do you have to select site that is pristine so that you farm more fish and they take all the nature's oxygen and clean water? Or are you able to deploy on a site that is close to coast and questionable and yet farm fish? How scalable are you, and how mobile are you? And how can you adopt to the region around you and to the world in the global aquaculture space? Now, in the next part of my introduction, I want to talk about farming in the environmental sustainability. Now, the ESG governance in FFCS is very critical. You have to be sustainable economically. That means you can produce more. In closed containment, you prevent the rich nutrient organic waste from going back to the ocean. In Singapore, 30 by 30 is a vision for Singapore, and SFA, the Singapore Food Agency, is pushing a lot. Now, for food security, one must look at the accessibility of the food supply, one must look at the availability of food supply and its accessibility. And we need to further enhance our infrastructure, that there's an ecosystem of things that makes our food fish easily available. In its accessibility, we want to know, when you produce local, how competitive are you? Has consumer is willing to pay a price a little bit more for sustainable, wholesome fish, healthy fish, but they are also price conscious. Mentioned here in one of the articles that wrote about us, it says nuts and bolts sink or swim with innovation. So therefore, the size of things is critical in our production of food fish. All this closed containment floating system must reduce the use of sea space. It must reduce the production cost. It must eliminate all the negative impact on its environment. Now let's talk about Pre-Line. Pre-Line is a floating closed containment system with its innovative uniqueness on being a semi-rigid raceway concept. You can see from the concept there is a HDPE tube 55 meter in diameter of capacity 2,200 meter cube. So in this particular case, the method of with extended slot shaped tubes that forms the ingress for fresh air to the fish. The next is a salmon house. It's the concept of a simple bucket. Now this bucket is a rigid cylindrical shape with reinforced concrete. Now the reinforced concrete is steel fiber internally, externally, and then the styrofoam internally to give extra buoyancy. In this particular salmon home bucket system, they have a capacity of 1,000 meter cube, and it is said to be the world's first concrete floating fish farm. The next is the Echo Cage. The Echo Cage is a flexible cylindrical shape wall system with using heavy duty flexible wall. I think this Echo Cage claim, and they said to have 99% survival rate, which is very, very good. Now the next system, the fourth system that I'll talk about is the Aqua Farm Neptune. The Neptune is a system that is developed with smart sensors that continuously monitor the internal environment. Waste collection is also at the bottom where it is removed by a large single pipe. Now the fifth one that I would like to talk about is called the fish globe. It is completely enclosed structure. It is complete enclosed. So that it's airtight and that it's able to push water in and also be able to push and transport fish out during its harvest from the tank. It has a capacity to be able to hold 2,000 tons of fish. It works out to be a stock density of 66 kilo per meter cube, which is very impressive. Now the sixth system that I would like to talk about is called the fixed closed cage floating closed containment. Here's again a lot of smart system in it, and it can hold a large capacity of up to 10,400 meter cube with a diameter of 160 meter. And additional buoyancy is from the 16-sided floating steel collars. So I think this is Aqua Farm, the Neptune. Now the seventh system that I would like to talk about is the Eco Arc. This is a system that I have invented and patented. Now it's waiting for global patent. Now it is a floating flow-through system. In this particular case, meaning to say 1,500 meter cube water flow directly through the 4 tanks that we have. But it has the ability to switch to recirculation system during the questionable time of oil pollution or during the time of toxic algae bloom or harmful algae bloom. It is a smart farm because we use a lot of sensory equipment, because it is fully enclosed and it is sheltered with a green roof. We can have all the sensor position and cleaning of it. It's easy. Calibration is done very easily. And it's highly productive because our stock density current is 50 kilo per meter cube. And it is highly scalable because 2 or 3 equal can be put side by side together. And it is sustainable. Sustainable because we have a responsible discharge. We do not discharge water directly from the culture tank. During its grow-up phase, we pass the water siphonic out by gravity through a discharge trough, goes through the drum filter, and then goes through a degas chamber where we put ozonated water to remove and gasify the ammonia. And because the solid particulate are then removed on my discharge. Our principal features are the dimension is a mere 48 meter by 28 meter length, which is the size of an Olympic swimming pool. And it has got 2 tiers, we call the main deck and the upper deck. But we have 30 more tanks, 6.5 meter cube, 6.5 meter cube, 30 on the upper deck for our nursery, post-nursery, and hatchery. Now we also have our own gas production system where we produce our own oxygen, we produce our own ozone, so that we can have the water treated with ozonation before it reaches the culture tank. So again, it is smart because we also provide automatic feeder system, and it is with a built-in photogalvanic solar cell, which means the solar panel itself is also the roof itself. Now, I would like to then highlight the article written by Singapore Food Agency to the World Aquaculture Society. The website can be found. It's called the Singapore Aquaculture Industry Contributing to Singapore Food Security. This is the chart taken from figure 7. It shows the typical farming system in Singapore. The open net, the tank above a wooden platform, the adopted floating barge, the smart floating farm, of which I added in the farming model for the future for Singapore coastal water. It's aquaculture 1.0, 2.0, 3.0, and 4.0. The 1.0 using the open net is a traditional farming method currently employed all over Singapore mostly, but they're still heavily reliant on the nature, especially for them to grow their stock. Aquaculture 3.0 land-based RAS system or the floating barge system, automation is there, and the system also able to monitor the water quality and also have a better husbandry technique. Whereas in the aqua system or the Eco Spark that we are talking about in the future, which is the future of farming, we use a game-changing technology of having a novel offshore advanced house system where the platform holds a tank below the water level. And because it's below water level, the water pumping rate is so low that there's very little energy required. And currently we're aquaculture 4.0 because we hatch the eggs all the way in our upper deck and we grow them out to juvenile, and we put them into our 4 big tanks, which is 500 meter cube each, and we grow them up within the 4 months. We get 400 gram fish that we harvest, and then we process them directly on board. We're also the first farm in Singapore that have a post-harvest processing plant, and it is licensed by the SFA, and we are able to do in one shift 500 pieces of fish every day, so that we can sell fish fresh. In my conclusion, I think we believe that the near future of floating fish farm closed containment system must play a significant role, that it must be able to not just be on the open sea in the deepest ocean so that the nature can wash away its waste from the fish, but it must be able to significantly protect the environment in both coastal and offshore deeper space. And on the design of a floating closed containment system, one must be able to look into any water embodiment. From the fresh water, you're able to be by the river, by the reservoir, or in the lake. On the sea, it can be any coastal to deeper sea. So the benefit of the FCCS, the floating closed containment system, are it relieves the land space for the population as the world population grows. And the FCCS is also a proven technology now because of the high yield that is environmentally and ecologically friendly, and it must be scalable, and like I say over and over, it must be sustainable to adopt the green energy, and it must also use nature and not borrow the future nature by using the oxygen and the clean water and return it back in a questionable way. So I think with this, the future, the near future of an opportunity for closed containment aquaculture system will be the way going forward. Thank you very much.
Thank you for the excellent presentation, Ms. Leow. If there are any questions, we might be able to take one or two. If you do have a question, you can put it in the question and answer section. While we are waiting before we go to the next presentation, I have one question, Ban Tat. RAS has been around for many years now. Why hasn't aquaculture in the ocean moved to the use of more contained, closed systems earlier? What is your opinion on this? Is it design or economics, or why hasn't the ocean aquaculture industry moved to a more containment system earlier?
Yeah. First, I must thank you, Professor Dean Jerry, for your kind introduction, and I thank you for chairing and leading this session. I think to answer the question on RAS system versus close containment, and why is it till today, then there are more talk about close containment. I think you're quite right. Number one, I think it's the economics of things. In the recirculation aquaculture system, there's still a lot of question about the capex cost and the cost of being able to reduce energy in the water treatment and circulating water around. And why have many not moved into close containment floating? I think it is one of the reasons why I went on to invent the Novus Eco. The reason is I think I am very thankful that I saw the gap in the aquaculture space. And then as an offshore and marine engineer, namely I've sailed around the world many years, I saw that the floating close containment concept that have been developed mainly are singular, big. So that's why there are many, cheaper versions. There are many versions that comes with tarpaulin, semi-flexible hull. And I thought that in order to be able to integrate the system, it must first comes to adapt the recirculation aquaculture system or water treatment. So my concept is water treatment, quality of water, quality of water, quality of water. So in the quality of water thing, it can be the water first must be filtered, and then it must then be ozonated or UV treated to sterile the water to remove pathogen and viruses. So I think, in my opinion, I think the idea has been there, but the engineering input from a naval architect and a marine engineer like myself probably was a little bit lacking. So I'm very thankful that I could develop the novel offshore advanced hull system, where the hull is submerged so low that the freeboard means the distance or the height between the water level to the main deck is 0.5 to 0.8 meter. And to do so, you need to have a very good buoyancy to hold it. So I think maybe by so doing, I'm able to create an integrated platform at a best possible cost over per meter cube of water that you put in close containment. I hope I've answered the question. Is there something that I should clarify?
No, thank you, Ms. Leow. That's an excellent answer. Okay, there are, we have one more new question, I think. Do we? We have a question, BT, from Philip Jackson. How does your system deal with the solid waste discharge and water waste treatment? Are the solids taken onshore, and how do you deal with the organic liquid waste? Yeah, currently what we have on our discharge, all the four tanks, the wastewater, or rather the used water from culturing, is being siphonic discharged to a discharge trough. In this discharge trough, we pass through the first stage of a drum filtration. Because we are in a Novus Equa, the platform is not, there's no sloshing, because we are fixed by two sputtered big sput pipe. We use a drum filter to remove the solid waste, and then it goes through a degas chamber, which is all the plastic, all the increase in surface area where we ozonate the water before it gets out. So to answer the question about how then do we take the sludge, the water that's taken out from a drum filter goes into our sludge tank. In the sludge tank, it basically helps sedimentation. It's being settled at the bottom of the sludge tank. We dewater them through a dewatering process and then pick up the sludge. So currently we are only producing, we target to produce 40 tons per tank per year. We estimate about 20 tons of slurry to be picked up and sent ashore. So we are currently doing just that. Did I answer your question well, Phil? Yeah, I think you've dealt with the question well, Ms. Leow. Okay, in the essence of time, I'm now going to hand over to my co-moderator, Dr. Leow Ban Tat, who will introduce the next speaker.
Thank you, Professor Jerry. Thank you for our first speaker, Mr. Leow, for your insightful presentation on the production technology focus in fish farming. And we're going to move to the second talk. We're going to be moving to the shrimp production in Southeast Asia. And our next speaker is Dr. Romi Novriadi. So Dr. Romi Novriadi is actually the Director General of Aquaculture. He is also the director of the World Aquaculture Society, the Asia Pacific chapter for the term 2019 to 2022. He is the vice chair of Indonesia Aquaculture Society for the term 2019 to 2024. He's also the senior researcher at the Directorate General of Aquaculture at the Ministry of Marine Affairs and Fisheries of the Republic of Indonesia. He is a published scientist with more than 25 peer-reviewed research articles in the area of his expertise that covers aquaculture nutrition, aquafeed formulation, immunology, aquaculture technology, and disease management. In addition, his PhD dissertation that focused on evaluation of advanced soy products in diets fed to Florida Pompano, and his master thesis was about a toolbox for immune parameters of Artemia, provide both beneficial information to the aquaculture industry. Dr. Romi was awarded 2 scholarships. The first scholarship, the VLIR UOS, to pursue his Masters of Science in Aquaculture at Ghent University, Belgium, and he received the Fulbright Scholarship to pursue his PhD in Fisheries and Allied Aquaculture at the Auburn University, Alabama, USA. Currently, Dr. Romi focuses on the development of a shrimp farming system, the determination of nutritional requirement for marine fish and shrimp, as well as facilitating the investigation of novel ingredients and feed supplemental properties to enhance the growth and health status of marine fish and shrimp. He is also the founder of super intensive farming system for a Lycopenius vanemi cultured in the concrete tank. And today he's going to be presenting his work on the production and recent technologies developed in the shrimp industry in Southeast Asia. Dr. Romi, please.
Hi, everyone. First of all, I would like to say thank you to the World Aquaculture Society for inviting me to this conference and for giving me the opportunity to talk about the production and recent technologies development in the shrimp industry in Southeast Asia region. My name is Dr. Romi Novriadi. I'm the Vice Chairman of Indonesia Aquaculture Society and also as the Director for the World Aquaculture Society Asia Pacific chapter. I would like to start my presentation today with an overview from the Global Aquaculture Alliance survey on 2019 about the production trends from 2000 to 2017. Based on the previous goal surveys, the industry saw signs of recovery in 2016 and 2017, resulting in a compound annual growth rate of 2.2% for the period of 2012 to 2017. From the global perspective, the graph saw an increasing trends in terms of the shrimp farming productivity. If we focus on the Southeast Asia region, we also notice an increasing trend in terms of the production quantity. There is a slightly decrease on 2015, but mostly due to the disease infection. After all, production has recovered since 2016 and reaching 3.75 million tons in 2018 and potentially for more than 4 million tons for the next coming years. Growth will be stronger in the Southeast Asia region, primarily due to several targets that has been set up by the government for several countries in this region. For instance, Indonesia already set the ambitious targets of increasing the country's shrimp export earning by 250% by 2024. Vietnam has a target of 10 billion shrimp export by 2025, meaning that from 850,000 tons of shrimp during 2017 to 2020, they need to expand to 750,000 hectares with 1.15 million tons by 2025. Thailand and Malaysia ready to start the production again and focus on the control of the ESPND and other disease, as well as to improve the water quality for better productivities, a better production system. Philippines, they would like to increase the production growth to be the top 10 of shrimp producers in the world. We know that right now, the recent trends in the shrimp culture in this region has been towards the intensive forms of the culture system, characterized by the use of the post-larvae from the registered hatchery and free from disease status, relatively high density, and have non-overlapping generation of shrimps. And but mostly, if we use the intensive culture system, we need to involve several technology. The technology including the feed management system by using the sustainable ingredients, functional feed or feed management, water management system that include the aeration system, water treatment and online data recording, biosecurity system, and also enhance the culture system using the nursery and also the millennial and concrete system. About the sustainable ingredients, we need to cut the feed costs. Diets has been developed based on sustainability and plant-based protein source that replace the use of the animal meal, especially fish meal, and several plant-based protein has been used to replace the use of animal meal, such as soybean meal, cottonseed meal, corn protein, and canola meal. If in the past, almost 69% of the animal meal used as the primary ingredients, with comprehensive research right now, around 53% plant-based ingredients has been used and only 31% of the animal meal used in the diet formulation. In the future, we would like to reduce more the inclusion level of the animal meal and increase the use of the plant protein source complemented with the novel ingredients to enhance the nutritional profile of the plant-based ingredients. We have a research at the Club Petit Mariculture Development Center. The 16 pond with size of 0.1 hectare per pond to be cultured following the commercial protocol of shrimp farming in Alabama, and our amino acid profile so that there are no significant difference in terms of the essential and non-essential amino acid, meaning that there is no significant impact to the protein quality of the diet when we try to partially and completely replace the use of the animal meal. If we look at the data of over 16 weeks of production period, we do not see any significant difference in terms of the final weight, yield, and survival, but we do notice significant difference in terms of feed cost and dollar per kilogram of feed. Nowadays, feed technology in the Southeast Asia region also moves towards the use of the functional feed to provide important nutrients that can help to protect shrimp against diseases. This data was taken with permission from Dr. Loc Tran Lab in Vietnam using high-protein DDGS that contain 25% of yeast and fed for the shrimp for 21 days of feeding period, 1 day of challenge test, and 10 days of observation after the challenge test. The use of 25% yeast and high protein content could have to increase the survival rate after challenge with Vibrio parahemolyticus strength ESPND. The next step to increase the production efficiency is a proper feed management system. How we apply a proper feeding regime in order to enhance the growth of shrimp. There are several techniques that we can apply, including the hand feeding system, using automatic feeding system, and nowadays several farms in Southeast Asia region already apply the sound-based feeding system. The sound-based feeding system could optimize feed utilization to improve growth and feed conversion and produce a better quality product. Regarding to the sound-based acoustic feeding system, we have performed a comprehensive research at the Club Petit Mariculture Development Center to evaluate the effectivity of this system compared to the automatic feeding and also the hand feeding in our commercial production facilities using 16 ponds. And our results show that the use of the sound-based feeding system could increase the biomass and growth and also cut the production period compared to the hand feeding system or traditional way of culture. Next technology, we need to more focus on the most reliable means of controlling the dissolved oxygen in the water. Therefore, there are a lot of innovation and technology development focused on the tools that can increase the solubility of the oxygen in the water. Future application on dissolved oxygen sensors that has been applied right now is how to connect the sensors to the oxygen tools, so that if the dissolved oxygen level below the acceptable range, it will automatically turn on the pedal wheel or other tools to increase the dissolved oxygen. Farmers right now also utilize the 4.0 technology by using mobile data that can sync the data to the cloud system for better and easy access. Several applications also cover the feeding, the mortality, the weight, the harvest, quantities, and other water parameters analysis. And the service and analytics also cover the remote monitoring with notification, biomass estimation, and also the growth performance. Many farms right now using this technology, including in my production farms, and data from sensors could have the farmers become more smart and efficient to make decisions during the production period. Still on water management system, several concepts to stimulate the natural estuarine condition by creating zooplankton blooms as the supplemental nutrition to the culture stream and beneficial bacteria to maintain the water quality already applied and used by many farmers in this region. For instance, in Indonesia, the concept of symbiotic being applied that involves the fermenting prebiotics, generally rice bran, and probiotics with enzymes to improve the pond environment condition. Several benefits that can be obtained by this system, including the disease control, the water quality control, improve the water quality, and also contain the fuel to sustain the good bacteria and provide soluble nutrients for the microorganisms. Other system now that being popular in Southeast Asia region is how to culture the shrimp using the sustainable biofloc system and also using the aqua mimicry concept that become more popular in Southeast Asia region and also mixotrophic culture system. Biosecurity now being massively used and applied in Southeast Asia farming industry, and this consists with the practices to minimize the risk of introducing the infectious agent or infectious disease and spreading it to the animals at the facility, and also how to avoid the risk that infectious agents will leave the facility and spread the disease to other sites or to the susceptible species. It is important to have better pathogen management by not sharing the equipment. Here you can see on the slide, and also manage the people and equipment by this using the disinfection food bath, and also spread, and also using the specific pathogen-free shrimp as part of the biosecurity program. Right now, in several countries, such as in Vietnam and Thailand, the use of nursery becoming more popular to minimize the disease outbreaks, since the outside nurseries can help to conditioning the post-larvae before stocking to the grow-out pond. But two things need to be remembered, become our primary attention. First is the density, and the second one is how to minimize the stress of shrimp during the handling and transportation process. Therefore, proper density need to be applied and the facilities need to be close to the grow-out ponds. In order to increase the productivity, right now Indonesia also introduced the new concept, what they call as the millennial farming system. In this system, commercial ponds supported by a lot of 4.0 technology, from the water monitoring system for the feeding management system, all integrated into one 4.0 technology to increase the productivity. However, if we talk about the challenge, there are two top challenges in Southeast Asia region. First is the broodstock quantity and facilities, and the second one is the disease outbreak. There are several broodstock facilities located in Southeast Asia region, such as in Aqua in Thailand, in Vietnam, also Vietnam and Indonesia, Global Gain Indonesia. But the production units located in Southeast Asia region still cannot produce enough post-larvae to fulfill the market demand. So with future ambitious targets and expansion, Southeast Asia region need more broodstock facility, especially access to the disease-free broodstock. And the next challenge is the disease management. We know that there are so many diseases become the main challenge for the production sustainability, including the acute hepatopancreatic necrosis disease, yellow head disease, Taura syndrome virus, white spot syndrome virus, and myonecrosis virus. How to overcome this disease? Many scientists right now focus on several techniques, including the quorum quenching, how to block, to inhibit the communication among the bacteria, and also the use of the epigenetics beta-glucans as the prophylactic approach to increase the cellular response of the immune system of the shrimp, polyphenols, biofilm system, and probiotic system. But the challenge is how to transform these promising results obtained from the laboratory scale to the commercial scale of the production system. This becomes the main challenge for shrimp industry in Southeast Asia region. So as the conclusion for my presentation today, technology has been identified as a driving factor to increase the productivity of shrimp production system in Southeast Asia region. And there is an urgent need to establish the captive breeding program for specific pathogen-free, specific pathogen-resistant, and specific pathogen-tolerant broodstock other than Thailand, Vietnam, and Indonesia. 4.0 technology often increase the productivity by improving the input and output ratio, thus resulting in a new production function. And challenge now is on novel technology development to overcome the disease problem in Southeast Asia region. So thank you for coming to my presentation today, and also see you all in Singapore on June 14 to 18, 2020 for World Aquaculture Conference and Exhibition. Thank you, and thank you, everyone.
Thank you very much, Doctor, for your very insightful presentation. We have quite a few questions. So the first one, which is related to the very first part of your presentation regarding nutrition. I believe Mr. Gopal Mitra question would be, what are the most important recent advances in freshwater aquaculture nutrition? Dr. Novriadi, are you here?
Hello, Dr. Leila. I'm here. Can you hear my voice?
Yeah, I can hear you very well. Did you hear the question? Right. Were you with us?
No. Could you please repeat it again?
Thank you very much for your insightful presentation.
All right.
We have a few questions for you. The first one coming from Mr. Gopal Mitra would be, what are the most significant recent advances in the freshwater aquaculture nutrition?
The most advantage for freshwater. All right, but we know that the freshwater species is for food security, but most of the farmer in Southeast Asia region consider the marine fish and brackish water as the business as usual. So the thing is, if we develop the freshwater nutrition, it's also good to balance the system between the business and food security. So in Southeast Asia region, normally there are a lot of place to develop this freshwater species, but it's not become the main priority right now because most of the businessmen also looking for the significant profit from the system. So normally the freshwater nutrition system only produce in the middle scale and small scale. Only few that concern in the big scale, but it cannot compare with the marine fish and also the brackish water culture system.
All right, thank you very much. We have another question, and this one comes from Professor Dean Jerry, the moderator, and his question is actually about the oxygen sensors. So he's asking how reliable and what are the maintenance requirements for these oxygen sensors when used in aquaculture pond environments with high levels of biofouling?
Yeah, that's a very good question, Dr. Dean. We facing several problems on that one, but we still improving the technology right now. We also working with the Singaporean company also because my home base is in Batam. It's only 1 hour from Singapore, and we're trying to improve the technology, how to increase the sensor sensibility and sensor quality, and also overcome the problem what you said as the biofouling things and everything. And now it's still under develop, Dr. Dean. Hopefully in 2021, in our next production system, we will apply it and then we will update about the results.
All right, thank you very much. We have another question regarding biofloc technology, And Mr. Gopamitra is asking if this will help reduce the provision of farm-made feed given to fish or prawn.
Your voice is
it's very low.
Up and yeah. So now I can hear you. Can you repeat again, Dr. Leila? I'm so sorry.
Yes, sure. So Mr. Gopamitra is asking about biofloc technology and if it will help to reduce the provision of farm-made feed given to fish and prawn.
Yeah, sometimes people misunderstood about the biofloc concept, Dr. Leila, because biofloc system is normally only can be used by the species that can be cultured in the high turbidity situation, like like a tilapia or marine shrimp. But now people use the biofloc system for carnivorous fish such as the African catfish, or sometimes they also culture the Asian sea bass in the biofloc system. So this is a misconception about because people really think that the biofloc system can also reduce the FCR, but if they not put a proper concept of the biofloc system, they will not get this biofloc system in the good way. So sometimes it's just make the production become fail and cannot get a good results for the biofloc system. So the thing is, we need to understand more about the biofloc system, what kind of species that we can culture in the biofloc system, and how to create a better biofloc system by balancing the carbon and nitrogen ratio in the culture system. Thank you.
Thank you. Can you hear me very well?
Yeah. Now
right.
I can hear.
Another question is it feasible to replace 100% of fish meal with alternative protein, considering meat quality and growth performance?
Yes, Dr. Leila. I mean, I did many trials here, and not only in the laboratory scale, but also in the commercial scale. Even I culture my own shrimp with my own diet by using 100% plant protein source. I'm not using the animal meal. But the thing is, I'm not see any difference in terms of growth and also the health status of the shrimp. So the thing is, based on my laboratory scale analysis and also the commercial scale production system, I'm pretty sure that there is no significant impact to the growth of the shrimp, because shrimp, this is they eat everything, the omnivorous kind of species, and also grazer animal, the continuous feeder also. So it is also good to provide them with a specific nutrient requirement for them to grow, rather than use the animal meal to fulfill the specific nutrient requirement. So we can also replace the animal meal without compromising the growth of shrimp, and also without compromising the health status of the shrimp.
All right, we have another question, and this time it's about the prebiotics. So person asking the question says, how do you see the utility of prebiotics like oligosaccharides and beta-glucans in controlling pathogens and support health?
Yeah, we know that shrimp do not have innate and adaptive immune system, Dr. Leila. So sometimes they only rely on the cellular and humoral response for the shrimp. So, but we can also trigger the development of the cellular and humoral response in shrimp by introducing them with the beta glucan or with the lipopolysaccharides, in order to wake the cellular and humoral response up. And but the problem is the duration for this immune system going up is only in this very short period. In my research, it's only for 6 hours. So when we try to use the beta glucan in our production system, we need to complement them with the proper feed management system. So we need to pay attention that sometimes it's required less than 6 hours to maintain the immune system in the shrimp. So we need to pay attention on this, and then provide the feeding management by considering this interval, in the hours interval, to provide the food to the shrimp with these functional properties inside the diet.
Thank you very much. And from prebiotics, we're going to go back to oxygenation with Mr. Philip Jackson asking at what sort of tank scale, or at what sort of tank scale, and by tank scale he means volume or fish density, do paddle systems cease to be effective for oxygenation?
I don't have the detailed answer of this, Dr. Leila, but based on my, I'm so sorry, my throat is okay. So the thing is, based on my experience in the reproduction system, is the dimension of the tank is just like a half from the production tank. So this can also help to reduce and also minimize the effect of this oxygenation in the culture system.
All right, thank you very much. And I think we still have a couple of minutes. And Mr. Marius is asking, do you have an idea about the number of farms using the Millennium System in Indonesia? And have they been consistent in their production? So it's two questions. He's asking about the Millennium System in Indonesia, and if it's yes, if you have an idea about it, how they have been consistent in their production.
All right, so it is just launched on the August 2020, and this is the second cycle, production cycle, and the production quantity and also the productivity is quite good with this millennial shrimp farm. But then we still need to make a good evaluation observation, at least for 3-cycle production system. Then we can come up with the data to disseminate to the scientific world and also to the people that willing to use this millennial shrimp farm culture system in the future. But the thing is, so far after we have a 2 production cycle, we do not have any problem with this technology. Even the technology really helped the millennial farmer to increase the productivity. So the thing is, the idea is coming from the young people, young generation in Indonesia. This second generation of the shrimp farmer, and they are open-minded with the technology, and they are willing to put the technology as the basis of the production system. So we have a promising results so far, and then we are really excited to see the result until at least 3 production cycle.
Okay, thank you very much. And we're going to end this presentation with one last question, and it's about plant protein feed. So what plant proteins did you test?
Oh, so the plant normally I use the advanced soybean meal. So the thing is, when I formulate the diet, the traditional soy protein still become the priority, has the maximum inclusion level, like 30 to 40%. But then I supplemented them with this advanced soy, like a fermented soy, soy protein concentrate, and also with the corn protein concentrate to complement the nutritional value of the diet. So we know that the soy protein, they do not have methionine in the sufficient level, lysine in sufficient level, and then it can be complemented with corn, and with the proper blending, with the proper formulation, we can also still fulfill the specific nutrient requirement for the shrimp with the proper combination system in the diet formulation.
Thank you very much. And with this, we're gonna have to wrap up this session. Thank you very much, Dr. Romi Novriadi, for the very interesting and insightful presentation and for animating this this question and answer talk. And I'm gonna head it back to Dr. Dinjari to wrap up this session. Thank you very much.
Thank you, Dr. Basti. And great presentation, Romi, very enjoyable. That brings our session to an end, and I would like to thank firstly my co-moderator, Dr. Leow Basti, and the 2 presenters, Mrs. Leow and Dr. Novriadi, for contributing to this session, and to all of you for listening in. We now will be handing over to the new session moderators after a short break, only a few minute break, I believe, and starting the session on the hour in about 2 or 3 minutes. So please continue to stay online and listen to the interesting new session about nutrition and fish and shrimp. Thank you.
Singapore is a small urban nation with around 1% of our land set aside for agriculture. Where can we grow our food? In 2019, the Singapore Food Agency put forward an ambitious goal for sustainable food security in Singapore.
30 by 30.
30 by 30.
30 by 30.
Currently, less than 10% of our nutritional needs are produced locally. SFA aims to increase local production to meet 30% of Singapore's nutritional needs by 2030. Aquaculture is a pillar of Singapore's agri-food industry, striving towards this goal by employing climate-resilient, resource-efficient, and sustainable technologies. At the forefront of these innovations is a vibrant R&D ecosystem, comprising institutes of higher learning and research facilities, working to ensure that technology paves the way ahead for the aquaculture industry. The Singapore Food Agency has supported both land-based farms as well as coastal farms in a sea of ways, from co-funding R&D to supporting the adoption of new technology and future-ready solutions. By utilizing innovation, technology, and research to maximize efficiency and productivity in our offshore and land-based farms, we will be able to grow more with less and achieve our 30 by 30 goal, bringing Singaporeans a safe and secure supply of food for years to come.
Welcome everybody to our session this evening on nutrition in aquaculture with a focus on fish and shrimp. Welcome everyone to our session this evening on nutrition in aquaculture, focusing on fish and shrimp. It's a great delight to be talking today and hearing from some wonderful speakers. We've got Professor Brett Glencross and Dr. Albert Tacon speaking to us this evening. So we were just learning about how important it is to be supplying food for human nutrition in Singapore and the 30 by 30 goals there. But to be able to do that, we actually have to be able to provide the fish and the shrimp with the nutrition that they need as well. So I will introduce our first speaker for this evening. So Professor Brett Glencross is the Professor of Nutrition at the Institute of Aquaculture at the University of Stirling in Scotland. So he joined that institute in 2016. Over the past 20 years, Brett has worked in various academic, institutional and industrial roles throughout Australasia, the Middle East and in Europe. Throughout his career, he has worked closely with many major international aquaculture feed companies throughout Australia, Asia and Europe. Brett was one of the former editors of the Journal of Aquaculture Nutrition until 2016. He's also the current chair of the Scientific Committee of the International Society for Fish Nutrition and Feeding. Brett's research background spans the development and commercialisation of bioactives for use in feeds, the application of functional feeds for animal health, refining knowledge on bioenergetics, essential amino acids and fatty acid requirements in both fish and shrimp, the use of nutritional modelling strategies, and the development and evaluation of novel protein and lipid ingredients in both fish and shrimp. He has honours and master's degrees in biochemistry from the University of Western Australia and a PhD in animal nutrition from the University of Queensland. So now let's hear Brett's presentation on advances in nutrition for tropical marine fish.
Hi, I'm Brett Glencross, and in this lecture I'm going to talk to you about the advances in nutrition for tropical marine fish with an emphasis on Asian sea bass, or otherwise known as barramundi. Biological systems are complex. When we try and look at the different factors that can influence the feeding process and the impact of nutrition, there's a range of things that we need to consider. The actual feed itself is one factor, but also things like the genetics of the animal, its behaviour and activity, the systems we're farming and the environment within all cause a range of interactions that actually make it sometimes difficult to actually undertake valid nutrition research that has meaningful application in the real world. So how do we deal with that complexity? Well, the modern way is to use models to actually allow us to deal with that. If we just take a look at this sort of diagram here to understand the old and the new approach, the old approach used to be to define a hypothesis, test the hypothesis at each level of organisation within a system, conduct the experiment, collect the results, compare it with the hypothesis, and then refine our process. And this process of empirical research rarely looked at look at one or two variables at once with any degree of assurity. A modelling approach, we use a data on a whole range of organisational levels and develop an integrated model and use the model to actually construct a hypothesis. We then test that hypothesis by conducting an experiment, collect the results, and then compare those results with what the model suggested what was going on. And then we can use this to actually refine our model on a perpetual process. So we get a better assessment of basically a integrated biological system over time. Now, nutritional models for barramundi have been around for about a decade at least now. This is one that I published about 8 years ago. The advantage of these models is it allows us to look at the impacts of nutrition on the fish at a range of temperatures and a range of sizes, and with a range of different approaches to actually designing the feeds. But to give you a quick example of how this might be applied, so at 30 degrees, we look at a 100 gram fish that we can predict is going to grow about 2.88 grams a day. We know that the metabolic body weight exponent for a fish of that size at that temperature is going to be about 0.84, which means its metabolic body weight is going to be about 157 grams. That means its maintenance energy requirement is going to be about 7.4 kilojoules per day. A fish of that size growing that 2.88 grams needs to accumulate 19.14 kilojoules of energy. We also know that at that temperature and that size, the fish is about 61% efficient in energy deposition. Therefore, to accumulate that 19.14 kilojoules, it actually needs to eat 31.27 kilojoules. Therefore, the total energy demand is going to be the combination of that 31.27 plus the 7.4, meaning the fish will need 38.67 kilojoules per day to achieve that growth target. That same approach we can also use to estimate the requirements for protein, amino acids, and a range of other important nutrients in the diet. We can take that information and then use that to actually reverse engineer feeds as well. So for example, if we take 1,000 gram barramundi at 30 degrees, growing about 7.8 grams a day, we can predict that that fish will need about 160 kilojoules per day of energy. We can also predict that it will need about 3 grams of protein per day. Now, if we arbitrarily take a feed energy density of 18 kilojoules, it could be 16, it could be 20, I'm just using 18. What we know is because the fish eats to an energy demand, that 160 kilojoules is satisfied by 18 kilojoules by 160 divided by 18, meaning the fish will need to eat 8.9 grams of that feed to meet its energy targets. That because we know it's going to grow 7.8 grams and it's eating 8.9 grams, immediately we've predicted an FCR. That has also constrained the amount of feed the animal's going to eat. And therefore, if we know it needs this amount of protein and it's going to eat that amount of feed, then we can predict the concentration of protein required in the feed as well, 3 grams in the 8.9. The feed needed to have 34% digestible protein within the feed for it to be effective. That, what it shows is there's actually a close relationship between the energy demand and protein demand in terms of actually predicting how much protein the animal needs. In this case, you can see for this fish, it's about 19 grams per megajoule. Now, if we look at that 19 grams per megajoule, I'd actually argue that the requirement's not constant. One is we notice that these requirements change continually through an animal's life. They vary with age, size, condition, but also the demands are not an exact estimate. What I would suggest is that across this transect to this line here, is we get a response like this. The red obviously is the peak value, and either side of it we have some room for latitude. Unless we get too far, then we start seeing basically problems with nutrient supply. So how to apply this on a practical sense is to overshadow or overlay that red line with a series of formulations approximating that protein to energy ratio. So for example, in a 4 millimeter pellet, that might be 50% protein, 16% lipid. But in a 10 millimeter pellet, it might be a 40% protein and 26% lipid. So you can sort of see that we're getting into lower protein and higher fat diets as we go from small fish to large fish. Now, this application of using high energy diets in fish has already been tried in Australia quite well, where they're comparing for large fish, say 1 kilogram to 2 kilograms. We got much better performance with fish fed lower protein, high fat diets. They grew the same, just the FCR was a lot lower. About 0.15 decrease in FCR for every increase in 1 megajoule of digestible energy. Another recent observation or discovery is that we found out that Asian sea bass don't use starch very well. In diets that were formulated on an equal digestible energy basis, it was clear that they had a preference for using protein for energy. In fact, inclusion of starch seems to have a negative performance on protein utilization too. Some recent work that's been done with the University of Wageningen in the Netherlands on net energy models and comparing barramundi with carp has shown that basically barramundi don't derive any net energy value from starch. They basically almost get no net energy value from it. In fact, when we're looking at some molecular work that's been done, we can see that the animal actually down-regulates protein synthesis and up-regulates lipid synthesis in those animals that have had high levels of starch. So that observation of fatty livers and fatty viscera in Asian sea bass, well, it's probably largely to do with the starch content, and the starch is not adding much value to their energy intake. Some other recent work that's been done looking at phosphorus demands by looking at increasing replacement of fish meals, we've identified that there's been a range of mineral sensitivities that have been identified. In fact, in this study here, we can see that high levels of low ash poultry protein concentrate led to poorer weight gain, which didn't make sense until they actually went and reformulated the diets through fortification with calcium hyperphosphate. And that resulted in better growth, better FCR, better calcium retention, but no change in phosphorus retention. But the fish certainly did a lot better. This suggests that phosphorus requirements are actually a lot higher than originally thought for Asian sea bass, probably certainly getting in excess of 1.5 to 2%. So raw materials are a perpetual problem. Obviously, with the rate at which aquaculture is growing, we need to increase our access to a range of raw materials. And one of the observations is that this is some of the recent data coming out of FAO. One of the recent observations is that marine fish are a big user of global fish meal reserves. In fact, marine fish globally now use more fish meal than salmon. The only thing that uses more fish meal than marine fish is shrimp. So there's a range of studies being developed now to actually try and improve our ability to use a range of raw materials to actually reduce our reliance on fish meal. However, in doing that, there's a traditional approach that we use for assessing nutritional effects of ingredients based upon the original review written about 15 years ago by Glencross, Booth and Allen. And that focuses on the characterization, feed intake, functionality, utilization and digestibility of the feeds by the fish with different ingredients in there to understand how they are impacting the fish. That review has recently been updated and upgraded. It largely covers some of those key issues, but also it now provides some examples of what happens when you don't follow the right approach, and also updating some additional needs for things like understanding immune function a bit more clearly as well. There's a range of data sources out there now that giving us a good overview of the characterization and utilization and digestibility, particularly of a range of different raw materials. This compendium was published about 3 years ago that pretty much consolidates all digestibility work out there for Asian sea bass. There's also been refinements in the methodology that we've been using to actually develop these assessments, and also some advances in technology on our ability to predict them in real time or very rapidly using modern methods like near infrared spectroscopy. But you can see there's quite a substantial number of ingredients in this review that have been evaluated and have digestibility values for protein and energy, in some cases amino acids as well. That's allowed us to look at things like complete replacement, complete replacement of fish meal and fish oil in diets for sea bass. When we replaced fish oil, it had little impact on performance, except when the fish meal was at 0. Replacement of fish meal was a little bit more problematic. It was okay up until about 10%, and then we went over a cliff. What we were able to deduce from this is that these fish, they were reasonably large fish at start, 150 grams, that their requirements for a long-chain omega-3 are probably actually quite low, certainly lower than some other species we had thought. But it might be that if you satisfy their requirements when they're little, then they're a bit more tolerant when they're older. In this case, we were basically replacing the fish meal mostly with poultry meal and soybean meal, and the fish oil was replaced with rice bran oil. There's also been a lot of progress in understanding thresholds to essential fatty acids, EPA and DHA, and arachidonic acid in diets for Asian sea bass. We've now got a good understanding of where those thresholds are for fish of different size. We can sort of see that once you go over a threshold, though, that the animal does, but you do start to impinge performance quite significantly, and those effects can be seen very quickly, like within weeks, and it does lead to a range of physical abnormalities when you have very, very low levels. We have improved our ability to use alternative oils, things like rapeseed oil, or in this case, poultry fat. The use of poultry fat in diets for Asian sea bass was shown to not have any impact on performance at all. So complete replacement of fish oil with poultry oil maintained the same growth and the same FCR, but there was some significant differences in carcass and fillet fatty acids. In fact, what we saw is when we used the fish oil replacement with poultry oil, we ended up with the same fat levels in the meat, but there was an increase in monounsaturates and a 3-fold reduction in omega-3. But this reduction was non-linear, which supports the notion of selective retention of LC-PUFA, which suggests that there's preferential use of monounsaturates and saturates. We've also done other work looking at showing that their saturates are really poorly digested by this species. So you need to be careful if you're using, say, oils like tallow or something, or palm oil. So that's a bit of a quick summary for where we're at with some of the progress being made in the last 5 years on Asian sea bass nutrition. There's been substantial progress made on defining requirements for a range of different areas, and some new insights have emerged. Modelling is now proving to be a really useful tool to explore new ideas and concepts, and our ability to actually understand how we apply different nutritional strategies across different environments and different genotypes and so on. There's also accumulating evidence that shows that including starch in the diet is problematic. If you want a fish to have a high fat loading, then starch is a good way to do it, but we might need to rethink the way in which we look at the feed manufacturing process if we're going to get rid of starch. There's certainly evidence that basically if we get rid of starch, there's better growth of the fish. And revisiting phosphorus requirements has shown that for Asian sea bass, phosphorus demands are substantially higher than previously thought. So we need to be mindful of that. The fish meal and fish oil story, there's a range of considerations there. There's a range of publicly available databases that are now available that have value, it's on ingredient value. There's clear thresholds of palatability when we remove things like fish meal. And there's also clear thresholds for essential fatty acid requirements that we need to consider if we're taking fish oil out as well. And notably, both of these seem to impact on the qualities of the fish meat. And with that, thank you, and hope to see you in Singapore in 2021.
Thank you so much, Brett. So Brett, are you there? Will you be available to take some questions in a minute?
I'm here, Jennifer.
Wonderful, thank you. So before I pass to some questions, I just wanted to let everybody know that the co-moderator for this session is Mohammed Saleh Kamar, and I will be introducing him very soon. So before we do that, Brett, thanks very much for your presentation and for sharing the comprehensive level of work that has gone into Asian sea bass nutrition. So what would you say, Brett, are the key things that are outstanding research needs for Asian sea bass?
A lot of it's actually common with many other species, Jennifer. I mean, there's really emerging need for us to better diversify protein and oil sources, in particular looking at development of new omega-3 sources. As everybody knows, most of our omega-3 comes from fish oil, and we have some significant constraints there to developing that further. But there is some lights on the horizon in that regard with some of the microalgal oils and some of the genetically modified rapeseed oils coming into the marketplace. But they haven't really been evaluated much in things like Asian sea bass or many of the tropical species yet. So that would be one area which I think would be very important. The other one which is going to probably increase in importance is better understanding of discrete amino acid requirements and amino acid interactions. And the reason why I say that is as we increasingly replace fish meal with alternative proteins, we can very easily balance the digestible protein and energy levels of feeds quite easily. What gets a bit more difficult sometimes is to try and balance the amino acid profiles. Some of the major amino acids like lysine and methionine, relatively easy to do so, but some of the less well understood amino acids, like some of the branched chain amino acids, for example, are a little bit more difficult to manipulate and manage. And there's some interesting observations coming out with respect to the way that they are interacting with and driving feed intake, for example. So that's, I think, perhaps another key area we look at. It's going down the path of understanding amino acids and their demands and how they interact with each other, and also the raw material story, both on the protein front and particularly on the omega-3 front.
Thanks, Brett. That's a great answer to that question. I am not seeing any questions coming up from our audience. So if you've got a question for Brett, please type it in so that I can get your questions answered. But I'm going to ask another one. So, Brett, I know microalgae and oils from microalgae is a great opportunity for adding marine oils into diets. So when you're talking about amino acids as well, what's your take on the opportunities to be using synthetic amino acids and adding supplemental amino acids to meet fish requirements?
Synthetic amino acids work really well up until a point. Once you get up above around about 2.5–3% inclusion in the diet of crystalline amino acids, they're well utilized and there's no apparent problems with regards to protein retention and so on. But once you go up above that 2.5%–3% range, what we start seeing is a flood of amino acids into the free amino acid pool, and then the animal loses the ability to utilize it efficiently. So you sort of have issues going above that range. Now, fortunately, in most cases, when you formulate a diet and you need to supplement crystalline amino acids, you're usually not going much above about 1 or 2% anyway. So it's usually not a problem in practice. I've run experiments with salmon over here in Scotland recently where we've had the diet up to 15% crystalline amino acids, and the fish do okay. They just don't do as well as if you had intact protein sources. That's all.
Okay. So another question, looking like big picture, that was kind of micro picture. Big picture, access to fish meal, fish oil, and the energy that's going behind marine fish aquaculture development and growth of the industry internationally. Where do you sit on the availability of fish oil and fish meal to meet that requirement on a global scale, and where do you think the big solutions are going to come from?
I think with fish meal, there's some clear constraints. We've obviously reached peak fish with regards to extractable resources. It's been a big move by the fish meal industry globally in the last 5 to 10 years in particular, with the Marin Trust's independent certification systems coming on board. Now more than half of the fish meal in the world is independently certified as sustainable. So I don't see a lot of issues there with regards what we can access. Our main issue is just the volume. We're sort of seeing consolidation of the fish meal production globally at around about 4 to 5 million tonnes of production per annum, and fish oil production's hovering usually just under about 1 million tonnes per annum. And it's probably unlikely to increase anytime soon. The other interesting movement in that space is we're now seeing probably around about 20 to 25% of all fish meal and fish oil globally actually coming from recovered fisheries. So what I mean by that is when we're seeing tuna caught for canning for human consumption, for example, the frames and viscera and the waste is actually now being processed and captured to actually retain that protein and that those oils. I see that probably continuing more into the future. Now, obviously, if aquaculture is sort of getting upwards of around about 50 million tonnes of production now, then there's clearly some scope for recapturing the parts of the fish that we don't eat as humans and better utilising that waste resource. Well, it's not a waste resource, it's a co-product, really. I mean, there's been good development in places like the Vietnamese Pangasis industry. There's good use of that sort of processing waste in the salmon industry in Northern Europe. A lot of that sort of stuff is also increasingly being captured by the shrimp industry as well. And there's a range of things we can do with these side streams in terms of value adding them to actually create a bit more of a circular bioeconomy to recapture the value. I look at it as a way of, we've got to move into protein and omega-3 recycling, basically. And then because nutrients always get burnt off by animals through metabolism, it's a bit of a leaky nutrient cycle. So we've got to plug it with new nutrients occasionally. And those new nutrients can be things like, well, plant proteins have been great up until a point, but that's going to start competing with human foods and pigs and chickens pretty soon. But things like bacteria and microalgae, I think, are real shining opportunities in this space.
Thanks, Brett. That's great. I have a question from one of our listeners. So, with the trend to new novel protein, pressure to reduce unsustainable marine protein and oil sources, etc., do you think that the next big challenge will really be about maintaining fillet standard and quality for human consumption?
To an extent. Generally, we find that protein sources don't impact on meat quality too much. Oil sources do to a certain extent. We see a clear change in the fatty acid profile of the meat depending upon the changes in the diet. And that, of course, can have some clear impacts on the omega-3 levels, which, of course, is one of the quality parameters we value a lot in farmed fish. In terms of the flavour profile, we're not seeing a whole lot of impact in that area from using different types of protein sources, whether you're using, animal proteins, plant proteins, single cell proteins. They don't seem to be making a big impact on that sensory profile of the animal. So I'm not too concerned about that. I'm more concerned about our potential depletion of the omega-3 and really us undermining the message that fish are the best meat to eat because they're really healthy for you because of this omega-3. We don't want to ruin that story.
That's absolutely right. I want to keep eating high quality fish because I know it's good for me. I'm going to hand over to our co-moderator, Mohammed Saleh Kama. So Saleh, do you have any questions for Brett before we have a listen to the next presentation?
No, I don't have any question yet. Yeah.
Yep. Okay.
All right. Right. Thanks, Jennifer. I will introduce the next speaker, Albert Tacon. Albert Tacon is a founder and owner of Aquahana LLC in Hawaii. At present, he also works as an independent consultant specializing in aqua feeds and nutrition. He has a long history, over 45 years of practical experience as an aquaculture nutritionist with FAO and in over 49 countries, and has over 250 scientific publications and 1 patent. I think he has a very wide experience in this field, and he will be presenting us on the title Aquaculture, Nutrition and Health. And I think with that, we'll let Albert Tacon to do the presentation. Thank you very much.
Good afternoon or good evening, wherever you are. It's a great pleasure for me to be here to present to you today. Thanks to the World Aquaculture Society for inviting me, and also to the Aquaculture Nutrition Network and aquafeed.com for their continuous encouragement. The topic of my presentation today is on aquaculture nutrition and health. It shows the generalized production pyramid and relationship between culture and disease. This slide shows the relationship between stress, health, and disease. And obviously, if we have a nutritional feeding regime which is suboptimal, or we have a culture environment where the animal is subjected to variations in temperature, DO, or environmental stresses, then the issues of disease resistance and health become paramount. In this slide, we show how stress can have a negative effect on health and disease. The stress can result from a suboptimal feed, or it can result from an environmental stress such as varying water temperature, DO levels, or a deteriorating environment. All these can result in stress and can have a negative effect on the health and general well-being of the species we're culturing. In this slide, I show the major fish and shrimp stresses through diet, feeding, and culture environment. Dealing with the culture environment stresses first, these can include, for example, an open, unstable environment, suboptimal water quality, poor water management, toxic sediment buildup, algal blooms and crashes, or from competing bacterial flora and biota. In terms of nutrition and feeding, stresses may include suboptimal feed and nutrition, poor ingredient quality, the presence of anti-nutritional factors and toxins, poor feed management, over or underfeeding, or the presence of viable pathogens present within the feed itself. This slide summarizes what I've said previously, the possible interactions between nutrition and health. We can have environmental culture stress, or we can have imbalanced suboptimal feed, as I said before. But also we can have infectious disease agents present in the environment, or we can have parasites or injuries due to the rearing conditions or toxins present within the feed that can all have negative effects, including reduced feed intake and a general reduced nutritional status of the fish or shrimp, resulting in reduced fish and shrimp health and disease resistance. But also some of these changes in environmental culture conditions can also alter the requirements of a species for a particular nutrient. And also they can result in a deleterious effect on gut health and nutrient absorption. My presentation today is a very short summary of a new handbook on nutritional disorders and diseases of fish and shrimp, which I've produced and which will shortly be published by 5M. In general, nutritional disorders can be viewed at 6 levels concerning proteins and amino acids, lipids and fatty acids, minerals and trace elements, vitamin imbalances, anti-nutritional factors, and feed contaminants. And for each of these nutritional disorders, We can also look at their effects on external features of the fish or shrimp in terms of animal behavior, body shape and size, the occurrence of lesions or skin color, but also in terms of internal pathology, in terms of blood hematology, gut structure and function, heart abnormalities, general immunity and disease resistance, and also pathologies related to the liver and hepatopancreas, the muscle, bone development, and also the kidney and spleen. On a general basis, the majority of these nutritional disorders result in reduced growth and FCR, but also generally in terms of reduced disease resistance, health, and overall survival. Examples of major pathology signs include abnormalities in animal behavior. Examples including certain vitamin deficiencies, mineral deficiencies, amino acid deficiencies, or fatty acid deficiencies can result in abnormalities in feeding or swimming behavior. A good example being a deficiency of tryptophan, resulting in increased cannibalism and aggressive behavior in several marine fish species, but also a deficiency of pyridoxine, resulting in erratic swimming, irritability, spasms, and convulsions. Each of these particular nutrients have their own way of exhibiting their own deficiency signs. Another example being a deficiency of DHA in some larval species, resulting in shock syndrome or alterations in schooling behavior. But these are all features which have been widely reported, and in the documentation I illustrate the species where these deficiencies occur. This slide shows examples of eye pathology, either in the form of a cataract or exophthalmia. Again, here listed along the side are the various nutrients which have been reported to result in cataracts and exophthalmia. The important point being that each cataract is different depending on the species and also depending on the nutrient, and it's important that we do the typing of the cataract so that we can know exactly if it's due to a deficiency of zinc, riboflavin, or a deficiency of methionine. In this slide, I show skeletal pathology in the form of lordosis or scoliosis and the nutrients which have been found to result in some of these pathologies. Again, each of these pathologies are species specific and nutrient specific. In this slide, I show pathologies of the liver or the gill structure. Again, liver lipoid degeneration, ceroid accumulation is a condition which is frequently found with the use of oxidized lipids, especially diets which are low in vitamin E, which is the natural antioxidant of the body, which helps the animal protect itself from these free radicals and things like oxygen. Some classic symptoms here, like green liver, are symptoms which occur in certain marine fish species due to a deficiency of taurine, which is an essential nutrient for these species, and taurine is involved with the synthesis of bile. Other nutrient deficiencies here with gill abnormalities, gill clubbing, are things which are classic in some species, especially salmonids, with a deficiency of pantothenic acid. Again, the important point to remember, each of these, although here they are listed in a very general way, each of these nutrients are only occur in specific species, not all species. In this slide, we have major pathology signs such as fin and skin erosion or short body dwarfism, various amino acid deficiencies, fatty acid deficiencies cause fin erosion, and then what normally happens is that you get secondary infection with fungi or with bacteria, and we have serious disease outbreaks. But again, I've just listed here some of the reported nutrients which have resulted in fin and skin erosion, and also mineral and vitamin deficiencies which have resulted in short body dwarfism. Again, not in all species, but here examples are for salmonid species. This slide shows examples of heart pathology and pathology of the muscle related to nutritional imbalances, either due to fatty acid deficiencies, vitamin deficiencies, and mineral deficiencies. In the case of salmonids, resulting in heart problems, but also the effect of oxidized oil and a general deficiency of vitamins such as vitamin E on the ability of animals being able to protect themselves from the harmful effects of singlet oxygen and free radicals. This slide shows blood pathology signs relating to anemia and reduced hemoglobin levels, either due to specific vitamin deficiencies or due to the effect of oxidized lipids or specific mycotoxin toxicities. Reduced hemoglobin levels are also a common result of the anemia. Again, many nutrients can cause reduced hemoglobin levels, whether it's specific amino acid or fatty acid deficiencies, mineral deficiencies, vitamin deficiencies, oxidized oil, or also specific mycotoxin toxicities. In addition to anemia and reduced hemoglobin levels, we can also measure the hematocrit, and a reduced hematocrit is also indicative of various nutrient, of the same nutrient deficiencies as for anemia and hemoglobin. This slide shows the nutrients which have been found to have a negative effect on the immune system or the immune response capability and the disease resistance of fish and shrimp. You can see again there's a wide range of specific essential amino acids, fatty acids, minerals, and vitamins which have resulted in, which have been shown to have a negative effect on disease resistance and immune function. Oxidized lipids, again, present as a major hazard, but also again mycotoxins. Mycotoxins are the anti-nutritional factors found in plants. There are over 500 different mycotoxins already reported in nature, and the majority of these have a very negative effect on the health and well-being, as I will show in the next slide. This slide shows the reported health effects of 5 major mycotoxins in humans and animals in general. And you can see that they have effects on various tissues. Several of them are carcinogenic, others are hepatotoxic. All of them have a general negative effect on the immune system and also on the gut health and structure and function. And here it's important to mention that in particular some mycotoxins have been found to affect gut permeability and the tight junction between cells, which facilitates the entry of toxins from bacteria and from unwanted metabolites into the bloodstream. Other mycotoxins have a negative effect on the kidney or on the nervous tissue or on the reproductive tissue. But in general, it's these are things that are universally present in many of the ingredients that we use, and so we have to be cognizant of the levels and how and their effects in the species that we. It's important to remember that for optimum growth and feed efficiency, all fish and shrimp have a requirement for about 45 essential nutrients, be they essential amino acids, essential fatty acids, cholesterol, and phospholipids, depending on the species, minerals and trace elements, and also vitamins, and a few new potential candidates such as astaxanthin, molybdenum, silica, and also vanadium. But there is a requirement for optimum growth. But there is also an even higher requirement for optimum health and disease resistance for many of these nutrients, as I will show. This slide shows that there is a requirement for most nutrients for optimum growth and FCR. But also sometimes there is an even higher requirement for optimum health and disease resistance and well-being. And so this is important to know that many nutrients, apart from being necessary for growth and metabolism and producing new muscle, but also many nutrients have specific functional properties in terms of health and general well-being. And so in this slide, I show some of the reported functional health properties of key amino acids to show that apart from protein synthesis and growth and energy utilization, specific amino acids also may have roles in terms of osmoregulation, stress response, immunity and survival, ammonia removal, and metamorphosis. So it's important to remember again that amino acids they're not only needed for growth, but also they also perform many essential functions within the body, including functions related to general health and disease resistance. This slide gives examples of various nutrients and ingredients which have been used in feeds and have been reported as having beneficial health benefits to the cultured species, including specific essential amino acids, nucleotides, fatty acids, sterols, vitamins and minerals, but also other specific feed additives such as enzymes, emulsifiers, essential oils and organic acids, and also prebiotics, probiotics, alginates, beta-glucans, carrageenans, chitosans, lactoferrins, mannans, peptidoglycans, and plant extracts. Many ingredients which have reported beneficial health effects. But the important thing to remember is that most of these, they may help with the animal and help its health and overall survival, but they are not a panacea to actually remove that disease problem. The pathogen is out there, but many nutrients and additives can help the animal defend itself against them. To give some concluding comments, it's important to remember that stress is seen as playing a very negative role in the overall health and well-being of most farm species. And so anything that we can do to minimize stress, to produce a more stable and constant environment for the species, the better. The more we can protect the species from pathogens present in the culture environment, the better. And so what is going to happen more and more, as has happened in the poultry sector, is the need for greater biosecurity and environmental control to minimize stress and also pathogen access. This is my final slide. It shows on the left side how the poultry sector was able to move indoors. It moved indoors to deny access to pathogens which existed outside, and also to create an environment, a constant environment where temperature and humidity were maintained at a certain level and where the animals had access to food 24 hours a day. In aquaculture, this is happening more and more with fish culture systems, RAS systems, where we can control the temperature, where we can control the environment, where we can eliminate entry of potential pathogens. And also with shrimp farming, more and more we are doing the same. But the message here is full biosecurity, environmental control, and by so doing, minimizing the stress of the species that we're culturing. And so with this, it's not a solution for all, but it's something where the aquaculture sector is learning very much from the terrestrial livestock sector and how that sector has been able to manage their biosecurity and disease management. And so with that last slide, so thank you, mahalo, for staying with me till the very end, and also to the Aquaculture Nutrition Network and aquafeed.com for their support. This is my very, very last slide. So again, thank you to the World Aquaculture Society for organizing this meeting. Here's hoping to see you all again in Singapore next year from June 14th to the 18th, 2021 for the next World Aquaculture Congress. So thank you and stay safe and take care, everybody.
That's a very comprehensive review by Albert on the fish nutrition and health. Yeah. As I've been informed that Albert will not be around to live to answer any of your questions. With that, I would like to return the mic to Jennifer, probably to accept more questions and also wrap up the session. Thank you.
Thank you, Saleh. Thank you so much. So I'm just wondering whether Professor Brett Glencross has got any final comments that he would like to make from an expert point of view on the presentations today. No comment from Brett. I've got a few questions here that are coming in for Albert. So Brett, are you able to take any questions?
I might be. I was just, it wasn't a no comment, Jennifer. It was a case of me unmuting.
Oh, okay. Yeah, please make some comments and I'll have a quick look at these questions.
No, look, nothing specific comments. I always love Albert's talks. And he gives a nice, thorough overview of things. No contentious issues there. It's nice to see him update the table there on showing the various nutrient requirements for fish and shrimp. Yeah, I mean, there's nothing really much more to add than what he's already said.
Okay, thank you very much. Maybe you can have a go at a couple of these questions, though, on Albert's behalf. Not that we would speak for Albert. So in your opinion, what's the most promising functional feed additive to prophylactically support immune competence and disease resistance?
From my experience, there isn't just one. There's actually different additives for different reasons. The omega-3s have a really key role in inflammation management, for example. Nucleotides play a really important role in cellular proliferation. Beta-glucans play a really important role in immunoglobulin activation. There's a whole range of things which come together. There is no one band-aid to cover this sore. There's multiple things we need to apply to actually deal with this. The most important one being actually just keeping the fish stress-free and healthy in the first place so it doesn't get sick. So instead of actually fixing a problem, we're avoiding a problem happening. That to me is the biggest message to try and get out there is, try and back off from intensification too much in terms of intensity, keep the water quality high, keep pathogens out.
Great. That kind of leads to the next question that we have. So we have another question that's very linked to that. The question is, in farms, first stage diagnosis based on clinical signs is really important to find out a cause of death. And all of us have been to a fish tank or a shrimp pond and we've seen dead animals and go, okay, where do you even start to work out what the cause of death is? So how would you differentiate fish cause of death by nutritional disorders or fish death caused by pathogens? Where would you start?
First, I'd consult a vet because that's what they're trained for. although vets, from my experience, are usually never great at identifying nutritional disorders. They usually go mainly hunting bugs, from my experience, looking for what bacteria, parasite or virus is killing this animal. And in many cases, as we know with humans, the biggest killer of humans is actually not a pathogen at all. It tends to be actually dietary related. With dietary disorders, they're difficult to diagnose because they tend to be slow and amortized over time. So there usually isn't a smoking gun around when you actually see the animal dead. It's difficult to find that clear evidence. There can be, and not only that, but a lot of the dietary deficiencies, their etiologies are all have a lot of similarities. You know, gut necrosis, poor redox status in the animal, blindness, whether it's ophthalmia or cataracts. You know, as Albert showed in his talk, there's multiple causes of these things, so they can be really difficult to diagnose, and that's sometimes half the problem. Which is why you need to get a good vet in, and hopefully a good vet that's had some experience understanding nutrition as well.
Great. That's a very good answer. Thank you. Saleh, would you have any final comments that you wanted to make in response to those questions as well? Because I know you're familiar with this field.
Yeah. Not on this topic, but I would just like to ask Brett whether the nutritional requirement of barramundi change if they are grown in freshwater.
We don't tend to see a lot of change. There will be probably some minor mineral balance changes between fresh and salt water, but major changes to things like protein and energy balance, no. They don't seem to be impacted by freshwater or saltwater change. We did have a bit of a look at that with respect to things like taurine. I mean, taurine is a non-proteinogenic amino acid which plays a range of roles, but it is notably plays a role in osmoregulation in some animals. And it didn't seem to be impacted by whether the animal was in freshwater or saltwater. It was ambivalent. It does need it. Barramundi does need taurine in its diet, but it didn't seem to make much of an impact on how much.
Thanks, Brett.
Thank you so much. I think we have come to the end of our questions and discussion for this evening. So it's been a really informative session, learning more about the high technology developments that are happening in Southeast Asia in fish and in shrimp culture, and then learning about our nutrition and how important that is in marine fish and in shrimp. So I really thank you very much to Professor Brett Glencross, and thank you to Dr. Albert Tacon for their presentations this evening. Thank you to the co-moderator, Mohammed Saleh Kamar, and thank you all for everybody who has come to our virtual webinar event today. And I welcome you all. Look forward to seeing people face to face next year in June in Singapore. Yeah, looking forward to it. So stay well, stay safe, and thank you very much for everybody joining today.